Hello folks. Today we're going to actually be starting with chapter 8, right? And as I would normally tell you in class, if you want to, right, just to separate out your notes from chapter 7 material, just fold over a piece of paper like this to make a divider, and maybe label it chapter 8. We're ever so slightly ahead of schedule actually. This is basically what we're doing for this week, all right? The graphs of trigonometric functions, which are also known as periodic functions, all right? Basically, right, this is what we will do today. These two comprise section 8.1, all right? And the remainder of these, tangent, cotangent, secant, and cosecant, these will be graphs for section 8.2. We're going to leave that until our Thursday class and just simply do these two today. Hopefully that is in the frame. I have to, let me just move this over so slightly. There we go. There is a handout that I would give you normally, all right, that basically consists of these 3 pages, all right, for section 8.1, all right. If you can, try to print out a blank sheet that looks like this. The links I'll have available in Canvas, all right, because there's a lot of terminology that we have to cover first. All right. There are also, all right, this page, which are 2 blank diagrams. I'm going to guide you through the process of drawing, because basically it's forming a reference for you. All right. And then a last page, which is a description basically of how to set your calculator, right? Assuming you have a TI-83 or 84, all right, to draw these things so that you don't have to keep reinventing the wheel, okay? So try to print out those 3 pages, okay? Let me put that aside. All right. Let's start with this, all right? A little review. I'm going to erase this. We have, to this point, discussed the subject of transformations. Right, things that you can do to a graph, essentially, to manipulate the drawing. Right? And the model that we had established, let's just call this the old model, that we keep adapting, right, looks like this to start with. If we're calling something a function, right, then in function notation, it would simply be this, right? An italicized f and a parentheses and then the input variable, which is x. Just bear in mind, this is a fancy way of calling something y. All right. And then the rest of the model looks like this. I'll try to draw this like so. There is potentially a plus or a minus up in front. A variable attached. Let me see if that is faint. No, that's visible. Good. And then the actual guts of the function, which I'll make like this. I'm always dubious about my green marker because it never seems to write so well. B, the actual variable, x, right? Then a sign. And then remember we have these other 2 transformations, close parentheses, plus, let's make this the same color. I wish I had more colors than just these 4. Okay. And you know, potentially, right, by now, that basically these pieces, if you will, of the transformation model have specific jobs, right, for affecting the graph of some function, right? You may, in theory, have all of these positions filled in with some number, all right, or maybe one of them, or maybe none of them, just the letter x, right? The most simple function would be y equals x, right? And you get a perfectly 45-degree diagonal line, right, on a coordinate plane, right? What we're going to do, all right, is translate these for the sake of sine and cosine respectively. Right? So we'll have, erase this to get it out of the way, a new model adapted from this. In theory, technically two of these, but I'm going to draw it right underneath the traditional model that we have for transformations, for sine and for cosine respectively, so that you can see the analogy between them. So to expedite this, I'm just going to go ahead and call it y, and then the second one y, and give it the same features. Right. I use capital letters, they tend to in this case. The actual function, the function of sin, right? Or cos, cosine respectively. And then the other features here, capital B, capital B, and let's see, the variable again is, instead of theta, a lot of times they'll just use the letter x, right? And instead, in lieu of function notation, they'll just simply put y, which is a little bit more normal, right? C, and then just squeaking it in here, these last two. Capital D, capital D. The one nice, I shouldn't say the only nice thing, but one of the nice things about the subject of math, at least if it's taught nicely, I feel, all right, is that there's a lot of symmetry, all right? You may have noticed since the beginning of the semester, we keep bringing up the subject of transformations, right? And we keep adapting this model somehow, depending upon whether you're dealing with a regular linear function or a quadratic, all right, or more recently, the logarithmic and exponential functions, all right? And now the sine and cosine, respectively, all right? Anyhow, there are jobs, again, associated with each of the numbers that sits in the position here, 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 and here, and also the signs technically, right? They changed the graphs somehow. That is exactly going to be the same thing when you get to the new model for trigonometric functions, all right? They just changed not only the symbols in the model to capital letters, and they refer to them according to the waveform names because these produce waves. All right. Let me give you a review of the terminology first. Maybe I should draw you a picture first. All right. I'm going to have you basically take out this diagram first, all right, to give you some satisfaction. All right. Let's draw these two diagrams first, okay? And then I'll come back and fill in terminology. So sometimes it's nicer to have a picture up front. More or less, save this information, right? I'm going to tell you specifically what the jobs and the labels are for these positions in the model. Okay. The duty, if you will, the obligation, vocation. Okay. Let's start with this. Basically, these types of functions, all right, trig functions, especially the sine and the cosine, produce waves, all right, as a graph. Okay, so give you the satisfaction of seeing that, all right. I'll have you draw this, or just basically doodle on top of the diagram that you can print. Right. This is all derived from a unit circle. So if you can imagine a unit circle drawn immediately adjacent to sort of a coordinate axis here, coordinate plane. Okay. I have to sort of simulate this freehand, so bear with me. Okay. I could draw a straight line to save my life. Okay. If you were to basically unravel a unit circle, and remember a unit circle should be sitting here, is defined as having a radius of exactly 1 unit. Right? If you were starting from standard position, which would be 0 degrees, right, and rotate this way, the normal situation, which would be counterclockwise, right? As you get from this point on the edge of the circle up to this point, right, as it's unraveling, you begin to see wave pattern, right? That's what I'm going to doodle adjacent to it, right? Basically, from here to here, tracing along the edge of a unit circle, you get this far up the wave. Right? To make it easy to draw, basically put dots at these points. A dot right here would be the origin. A dot right here at this first line, dash line here, right on the axis again, down here, and then above there. All right? These are key points that are a degree or a pi radian that in theory that you would want to memorize in the long run, right? If nothing else, develop a reference, right? Means if you do have it memorized, you can basically do calculations without your calculator. You could just make a prediction, an educated guess about something. Anyhow, as I said, if you unravel, right, a unit circle, right, over time, as you travel from this point here to this point here on the unit circle, this much of a wave would begin to form this way. If it's stretching out over time, time is basically the x-axis. Right? I may not call it time, I'll call it some derivative of pi, all right, or some other unit, but that's basically what it is, it's time. All right? Anyhow, as you keep unraveling the circle over time, you'll get to this point, which would be from here to here. All right? Now, if you remember from unit circles, all right, or circles in general, all right, this is 0 degrees here, all right? This is 90 degrees here, and this is 180, all right? And if you kept going, it would be 270 here, and then a complete 360, all right? That's basically what these points are going to be. At this location, all right, this would be 90, 180, 270, and 360 degrees, all right? Or you could refer to them, all right, in terms of pi radians, the equivalent. If this point here is at the location along the x-axis at 90 degrees, well, what is 90 degrees in pi radians, right? 90 degrees is pi over 2. Right? What is 180 degrees, all right, in terms of pi? Right? 180 degrees is exactly equal to pi. All right? What's 270? Right? 270 degrees, you'll see, is 3 pi over 2. A fraction of pi, an improper fraction, granted. And the whole kit and caboodle, right, of 360 degrees is 2 pi. Right? And now to complete this thought, as you move along this way, you fill in, or the wave gets further and further unraveled. Right? If I go from 180 now to 270, right, That's going this far along the edge of the circle from 180 down to 270. In terms of the wave, that's from here to here. All right. And then finally you go the whole 9 yards back to the start, basically, because it's cyclical. It's a circle. All right. From 270 to 360 is from here to here. All right. All right. The most important thing I could tell you, right, is that a unit circle unraveled, right, forms a sine wave, right, in its most basic form, right. You'll see cosine in a moment, all right, and there's really not much of a difference. It's just phase shifted, right, but it makes this wave pattern, right. Why? Because we're not just moving in circular motion, we're stretching that out linearly, all right. We're translating it to linear motion, if you will. Okay, anyhow, try, first of all, to label the diagram for reference, but also in the long run to know these key points, all right? What they are for a sine wave, because this is sine. Y equals sine of x. I think there's a little box on my handout, all right? What you see here. All right, just write for the function y equals sine parentheses x, right? And that's what this graph represents, right? Those 4 points, all right, translate to these 4 points, all right? Well, 5 points technically because it's 360 and 0 is the same place. Okay, we're building a reference. All right. If you're curious, all right, about these features, there's some extra information I'll just put here. The domain, all right, if we're using x again instead of theta to represent the angle, all right, the domain would be what the x values are naturally. Here it is in interval notation. If this is truly a wave of a sine graph, all right, then it's sinusoidal. There's another phrase for this. Sinusoidal pattern. It stretches into infinity, right? Like light does. Visible light, or light in general. Electromagnetic spectrum is sinusoidal. Here's the domain. It would go from negative infinity to positive infinity. I'm just starting here, but in theory, if I were to track backwards, the pattern, all right, would form into infinity back this way, and into infinity this way, because that is the nature of waves. All right. As for the range, right, the range is a little bit more interesting, perhaps. It's from negative infinity to positive infinity. Pardon me, I'm double talking here. Positive 1 and negative 1. The low bound is negative, the upper boundary is positive, right? If again, this originates from a unit circle, right? A unit circle has a radius, although it's distorted because of my bad drawing, right? But it has a radius of 1. So even as it stretches up this far, how far is it from the center, right? It's still the amount of 1 here. It would, in theory, be the amount of 1 here. It would be the amount of 1 here, and it would be returned to the amount of 1 there. Unit circles will produce a maximum of positive 1 from this line that it's riding along up to the high point, the max, all right? And in theory, from the middle line down to the lowest point, all right? This would be negative 1, all right? Know these two extrema, right? Positive 1, negative 1, positive 1, negative 1. It's always going to hit that ceiling and hit that basement, if you will. All right? This is a minimum. This is a maximum. Okay? Here's some other fun facts about this. Right? This would technically be referred to as an odd function. I don't know if you remember this from a while back. We have odd functions and even functions. And what that really is referring to is its symmetry, right? Meaning, what does the picture look like before and after you mess with it, all right? Before you've reflected somehow, all right? if it's an odd function, it means it has symmetry about the origin. And all that really means is that if you flipped over y-axis and then also the x-axis, it would look the same, right? If I flipped this over the y-axis, it would be flipping it horizontally like this, right? If I then did it again, flipped it over the x-axis, it would be reflecting it vertically. What you would end up with is the same waveform, right? Even in spite of doing that, right? Symmetry, it looks the same before and after those changes. But in the case of odd function symmetry, it has to be about the origin. It's two flips, one over the y-axis, one over the x-axis. Okay? Let's talk about this, the cosine now. This is sine. It's a very similar picture. But it's going to change the output variable, the output value, I should say. I'm going to have to try to duplicate this again, hopefully a little bit neater, right? It wouldn't hurt to use a ruler, right? Let's see. We'll do cosine now. There's again an empty space on this diagram, all right, here in red, all right, where it says function. Just maybe write y equals cosine of x. So we'll see y is equal to the cosine of x. Okay. Here is vertical axis, hopefully straight, and maybe a little bit better. Maybe I should look at it while I'm drawing it. All right. And horizontal axis like this. All right. Again, if this is derived from unit circle, try to draw a unit circle here adjacent. A little bit smaller, right? I'm going to simulate some vertical lines here as best I can, consistently as I can. Okay, and give you a couple of points to remember. All right, if again this is a unit circle, by definition a unit circle has a radius of r equals 1, right? Which means, once again, the maximum as you go through this waveform will be positive 1 and the minimum will be negative 1. Okay. For the sake of contrast, let me draw blue points. All right. There's 0 on the circle, there's 90 on the circle, there's 180, 270, and 360 is the same location. All right. If we are still rotating the normal way, which is counterclockwise, right? And we unravel this over time, we'll see the wave pattern that forms. In the case of a cosine, right, the whole thing, in theory, all right, would be shifted over by 90 degrees. I don't want to superimpose this red circle exactly where it ought to be, which would be here, all right? So I'm just going to keep drawing it next to it like so. But in fact, your drawing would start up here, all right, at the maximum of positive 1, right? So put a dot for the graph of the wave right here on what would be the y-axis normally, right? Put a second dot here now on the 0 line, which would be the x-axis, right? a dot here respectively, a dot here respectively, and a dot here. Okay. This is the difference between a sine wave and a cosine wave. Right? A cosine is what we say out of phase by 90 degrees. And I talked about complementary complementary functions like cosine, cotangent, cosecant. I use this phrase, I don't think I wrote it, but I think I said it a couple of times. Out of phase, it just means that it's out of whack by 90 degrees, all right? It means it's shifted over by 90 degrees. So it really is going to be the exact same wave. It just looks like this, right? From essentially a starting point, kind of an arbitrary starting point to be fair, all right? But you'll have a wave that looks like this. Again, if I backtracked it, right, it would look like this into infinity this way, and it would continue on in this waveform that way. Do know these key points, right? At 0 degrees, right? This is 0 pi, I guess you can call it if you really wanted to. 0 times pi is still 0, right? It is the maximum of 1, though, you know. This point here is 90 degrees. Let me put this in a different color because I don't think it's showing up. Sorry. So this is really at the location of 0, all right, this point here, all right. This point here is what would be 90 now, all right, in degrees, and in pi radians it would still be pi over 2, all right. At the location of, along the x-axis, all right, what would be 180 degrees, all right, down here is where the graph actually exists, all right. This 180 is exactly pi, all right. This point here, all right, is the next one, 270, which is 3 pi over 2 again. And then up here, which along the x-axis would be here, at this location, all right, we're talking about the x value, which would be 2 pi, all right, 360. Okay. So know these points, all right, what they correlate to in terms of degrees and pi radians, all right. 0 is 0, you could say 0 pi if you like, all right. 90 is pi over 2, 180 is just pi, 270 is 3 pi over 2, and 2 pi is 360. Those are these points respectively on the circle because this is unraveled, essentially. You took circular motion, or something circular, and you're trying to explain it linearly. Right. Circles unraveled produce waves. All right. Now, again, the two extrema that are important in terms of a y value, right? The maximum is 1, and the minimum is equal to 1. All right. That means that if somebody gave you a problem like, what's the cosine of pi, right? You could type this into your calculator, of course, and your calculator would spit out an answer. All right. This is an x value, and you're trying to figure out what the y value is. If you know these points, you've memorized them, right? You could figure out what the y value would be, right? The cosine of pi, according to this waveform, should be equal to -1 at this location. The cosine of 0 would be +1, because that's what the y value is at this location. What's the cosine of 2 pi, all right? Same thing, it would be because it's periodic, it repeats over and over again, all right? It would be the value of 1, all right? Cosine of pi, -1, all right? As proof of that, all right, you could take your calculator, clear this out, all right, I'm sorry that there's a little bit of a glare here, all right? And type in cosine of, unless your thing is, your calculator is preset to radians, all right? Maybe just type in the equivalence, which would be 180, all right? And you see what you get, all right? The cosine of pi, which is the same as saying cosine of 180 degrees, is -1. You don't need your calculator for everything if you know some fun facts. All right, truly fun, right? All right. Those are the graphs that are relevant to section 8.1. Okay, the sine graph and the cosine graph. All right. Try again, like I said. All right. Spit out this diagram. Fill in the respective information. All right. How the picture ought to look for sine. How the picture ought to look for cosine. All right. It will help you if you write this stuff out to memorize it without really trying too hard to memorize it. All right. Here again, just to complete this thought. If you wanted some fun facts about this, here's the same domain really. What are the x values for a cosine function? Well, it would stretch from -infinity to +infinity, right? What is the range? It has those two extreme y values. Remember, range is y. Lower boundary is -1, upper boundary is +1. Right? And in this case, this would be an even function, right? Because it has symmetry horizontal symmetry, which is say about the y-axis, right? Meaning it has horizontal symmetry. If you reflected this, right, about the y-axis, it would look the same, all right, having done just that one alteration to it, all right. In the case of sine, it has odd symmetry. All right, it's about the origin instead. You'd have to flip it over both axes in order to get it to look the same before and after. For these even functions, it has horizontal symmetry. You're just flipping it essentially over the y-axis. All right, another phrase that they get thrown around, all right, as I mentioned before, sine and cosine are complements, all right? The complementary functions, why? Because they're out of phase by 90 degrees, okay? All right, now let's go back to terminology. And to that effect, let me erase this firstly. And then I'll have you basically copy down some information to explain the transformation features. My markers are getting dried out, unfortunately. All right, save that. Okay, now let's go back to this. If you would, all right, you could either try to draw this or print this out, and we're going to fill in the terminology for the transformation features here. And I'm losing a page. I'm gonna take this down because I had to draw something. I'm gonna use my original fake whiteboard here. So, oh, the special effects. This is my piece of plywood. I doodled this just a little while ago. And I'll put my acrylic plastic on top of this. There we go. Fortunately, it's broken here, so I'll just see if I can rotate this. Is that okay? All right, good enough. Let's start with this. All right. To say that something is periodic, there's no symbol for that. It's simply to imply that it has a pattern. Okay. And then it repeats into infinity. for all intents and purposes. It is a pattern that repeats into infinity. All right. Now, I don't want you to draw this here, but I want to point at it, so I'm going to kind of scribble what the transformation model was, and I'll erase it later. Don't write the thing that I'm going to write, maybe in the middle here. Let's see. Here's our model from before. Y equals A. We'll start with sine. Bx minus C plus D. Right. I just want to be able to point to this as I'm going through the terminology. Right. We'll go in alphabetical order, that makes sense, right? Let's start with what A is. Right? A is the concept of amplitude, which is essentially the height of the wave. It would technically, it's either a maximum or minimum. If I had a wave, like from before, I'll just draw this very simply here. The maximum would be in relation to this line, which has a name I don't want to tell you just yet, right? But since this was riding along the x-axis in theory, right? The distance from the x-axis up to the maximum, or from the x-axis down to the minimum, right, is the amplitude. Right? So it's intuitively referred to as A, right, capital A. Right? In comparison to the transformations that we're familiar with, notice where it's sitting, right? It's sitting up in front of the function. Normally it's not written as sine, granted, but it's the first variable, the first number that in theory, the first constant, I should say, the coefficient that would sit up in the front, right? That is analogous to what we used to call as vertical stretch, right, or compression factor. The vertical stretch or compression factor, the thing that pulls the graph vertically this way, would be a stretch. All right. From this perspective, the vertical compression would make something wider this way, but it would be, in theory, pressing it like so. Right. In theory, this could, if you see something as being negative or positive, you don't really have to worry about it. Because it's a wave, it's going to be negative and positive. Anyhow, you could calculate it, all right? We're going to put this in absolute value lines, all right, because we want just the whole number value, really. All right? You could calculate it from the difference of the maximum and minimum, finding the absolute value of that difference, and then dividing it in half, all right? Multiplying by half is the same as dividing by 2, right? The entire distance from here to here, right, would be the number that shows up inside your absolute value, and then half of that naturally would be what the amplitude is. And it would be a number that would sit here, all right, in the model. The next thing is B value, all right, the number that would be sitting here in the model. This is technically, you're not really responsible for this. It would be more relevant in a physics class. All right. The B value has another symbol in a physics class. It would be the same job, but they'd use a different Greek character. All right. And it's the angular frequency, or the angular speed. I think we use that, I would say we, the royal we. Speed. Yeah. Angular frequency. I'm going to use that phrase. I like it instead. But the angular speed, the angular frequency, for all intents and purposes, same difference. And they would call it in a physics class omega, like this. There was a formula from, I want to say section 7.1, all right, that you could calculate the angular speed, all right, and it is using the Greek character omega instead of the capital letter B, which is what your textbook is using. All right. Anyhow, what is it as a concept? All right. In terms of a wave, all right, it's the number of iterations Iterations is essentially the number of clones, if you will, the number of times something occurs, repeats. It may be a little bit hard to see, so let me put this in capital. I really should say the word iterations. But I'll say times is kind of a colloquialism. Times, the pattern repeats. In one cycle. I'll put this in a little bit darker so you can see it. In one cycle. A cycle is one complete rotation, all right? One complete waveform, all right? The normal condition would be one complete waveform, all right? You may have something that repeats many times in what would normally be the same time frame, all right? It's a faster frequency. Right. Usually, right? Usually, I'm going to just kind of squeaking this in here. Usually, the time frame is 2 pi. Right. That's how long one cycle takes to complete one waveform, right? If you have something that completes one whole cycle, one whole waveform in a shorter amount of time than 2 pi. And that is just suggesting that it's a little bit faster in terms of angular speed or angular frequency. Same difference. All right. Anyhow, to calculate this, there's this sort of formula. All right. Again, the absolute value, all right, of B is 2 pi over P. And you'll see what P is in a little bit. Because this is a little bit off the thing here. Let me write this out of the way. I'll put this B here. Concept. 2 pi over P. All right. This is something that's called period. All right. I'm going to give you that definition a little bit further. But it's essentially a number. All right. That's going to be sitting here. You're going to divide 2 pi by a number. And that will give you what the B value is. And then you would insert it here in the model. Its job tells you how many wave patterns you're going to have, right? The number of iterations, the number of times the pattern repeats. And for sines and cosines, all right, the normal period, the normal time is 2 pi. When you get to tangent, I believe it's just pi actually. And for sine, 2 pi. Okay. And also for cosine. Okay. What does this correlate to, right? In terms of the traditional transformation, it's the horizontal, all right, stretch or compression factor, all right? What influences the graph basically by stretching it out horizontally this way, elongating it, all right, or squashing it, all right, horizontally, all right. Then there's this. I'm gonna have to erase this, but I'll draw this little circle here. The next letter naturally would be the letter C. What is the job of the transformation term or factor that's sitting in this specific location in the model, the C position, if you will, which is H in the traditional model. What is C? Okay. The truth is that C is dependent upon B. Right? You could refer to this as the phase shift. Let me see if that's visible. Looks like it's okay. Sorry for the squeak. Phase shift. All right. In the more traditional context, this would be called, let's see if that writes a little bit better, the horizontal shift. Which you know basically controls left or right. All right. When your graph is shifted left or right horizontally, right, it's a horizontal shift. All right. The thing is, because you're dealing with waves, right, which are periodic and they stretch into infinity in both directions, all right, the graph is going to be sort of deformed slightly, all right, and it is dependent upon really the B value as well, all right. So when you're doing a calculation to figure out what's going to sit in the C position, all right, just realize that you would have to, in theory, divide by B simultaneously. All right. If in theory, all right, there's no horizontal stretch or compression, all right, that is written like it's just the value of 1 potentially. That means that it's just C divided by 1, which for all intents and purposes is just C, you know. All right. And now, what does that mean? To clarify, I'm just going to erase this because I need the space. It means that you're either going to have exactly the same wave. No, that's so faint. All the greens are lousy. I'm going to write a letter to Expo. Right? That's what these mark is. Right? It means either the same wave, right, just shifted left to right, right, or distorted slightly. Right, maybe stretched a bit, you know. Right, because again, it's dependent upon that B value. Then there's this D, right? The next value, which is D. This is really easy, this one. This is referred to as the midline. And in the context of the traditional model for transformations, this is the vertical shift. Which controls up or down. Right? The phase shift is the horizontal shift, which controls left or right. Then the midline, which is sitting in the D position, we would normally call that K, strangely, right, is the vertical shift. That's a T, I swear. Okay. All right. Usually, this is essentially the middle of the wave. The axis, the middle of your wave, all right, and it's usually y equals 0, or you could call it the x-axis, right? If a waveform is shifted vertically, like so, all right, all that means is that the middle line upon which the wave seems to be riding, right, would be, you know, up 1, down 1. So the whole wave will be picked up a little bit, right? That would make the minimum and the maximums in different places as well. Now, the last thing as far as terminology is concerned is getting back to this concept here, period. Why are these so faint? I think it's just cold in my hallway and the markers are getting a little funny. All right. Period. Capital P. The P in this formula that you see for B value, all right? They're inversely proportional, all right? A period is basically time, all right? In other textbooks, they would use a capital letter T exactly for that reason. Just like angular frequency is omega in a physics class instead of a math class, period is, instead of it being a P, is a capital T, right? Because it is something like time. Right? It's not exactly, lowercase t is usually time in general, but capital T is period time. Right? What does that mean? It means the amount of pi which I'm just going to refer to as time to give you a feel. The amount of pi, because that's the x-axis instead of labeling it seconds per se. The x-axis is chunks of pi, basically. Right? It's the amount of pi, which you can think of as time, that it takes to complete one full wave form. Okay, a cycle is another way of referring to that. Sloppy cycle. Okay, so just to compare notes here with the angular frequency, the horizontal stretch compression factor, IEB, right? B is the amount of pi, which you can think of as sort of being an amount of time, all right, divided by the period, all right? That's the number of actual waves, if you will, all right? The number of iterations, all right? If it makes it more clear, convince yourself. The number of waves, all right, that the pattern repeats. 2 waves, 3 waves, 4 waves, what have you, in one cycle, all right? The period itself is the amount of time, all right, it takes to complete, all right, one full waveform, all right? Anyhow, that makes this dependent upon B, right, inversely. So if you had to, right, you could calculate it like this. 2 pi over the absolute value of B. See, it's a denominator in this case, the B value, and the P is the denominator in this case. Okay? They're inversely proportional. One is referring to the amount of time, one is referring to the number of waves. Okay. All right. Let's do some examples. Okay. And do remember, before I go away, this formula, all right, and this information, all right, 2 pi especially being the most important thing. This pertains to sines and cosines, right? This is for both sine and cosine. When we get into tangent, which is section 8.2, the formula changes a little bit. It's just it's dividing by a different period. And it's 1 pi, 1 whole pi rather than 2 pi's. Okay. All right. Now let's do a couple of examples. Are we on time? That's okay. I'm going to erase this. And then go back to my other whiteboard. This was the original background that I had been using when I first started shooting at home. So it's a little bit narrower. Anyhow, I'm glad I didn't throw it away, because at least I could draw diagrams onto it. I'm going to rotate my acrylic plastic now. Let's see, hopefully keep it out of trouble. Like that. There we go. And we're still in frame. Let me just adjust this slightly, perhaps. And I'll pull that back, not too much. I got my pocket protector basically propping up my camera. Oh, the madness. Okay, let's go back to this. Okay. Let me duplicate that model just again for reference. Y is equal to A sine bx minus c plus d. All right, and we know that these have specific jobs. Okay. Suppose you had this for a problem, and you were asked, right, given this, y equal, we'll just put it in function notation to be funny, yeah, hilarious. All right, the function is equal to the sine of pi over 6 x, and no other features. All right. Given this, to determine the period. Okay. Well, as we said before, see what's missing. All right. The amplitude is missing, so you would assume it's 1. All right. The C value is missing, so you could assume it's just 0. All right. Same for the shift. If it's missing, you could assume it's 0. In these cases, the terms separated by plus or minus, you have to assume 0 if they're not written. All right. In the case of the coefficient that is the amplitude, you would have to assume it is 1 instead, because if it was 0, it would just erase everything out of existence, right? So 1 is just filling the void. The only thing that is present is the horizontal stretch and compression factor, otherwise known as B, angular frequency, whatever you like. All right. So if we're going to calculate the period, here's a formula that we have established, all right, which is that the period is equal to 2 pi, because we're dealing with a sine or a cosine. This is the formula for sine or cosine, strictly, of 2 pi over the absolute value of b. All right. So we're going to insert the little bit of information we could pluck out of the example into this formula to calculate the period. If this is basically the b value, pi over 6, then in theory we would insert pi over 6 here, right? And it would be a positive because of the absolute value lines. Okay. Now realize what we got. We're basically dealing with fundamental arithmetic at this point, so don't even be intimidated. It's weird symbols granted, but this is a number divided by a fraction, right? So take that which is sort of vertically written and sort of stretch it out the more traditional way. Meaning, if you see this on top, then it's 2 pi. If you see this line, all right, use the traditional colon with the line for division, all right? And then put the sort of fraction-esque ratio we have here, all right, adjacent on this side respectively, all right? And then remember, when you're dividing fractions, keep change flip. Which means keep the first sort of fraction, just to make it look like a fraction, I'm going to stick a 1 under it. Change the operation to multiplication instead. I think this is drifting a little bit. Let me just fix this. And flip pi over 6 upside down. So you'll see this. 2 pi, just to make it look like a fraction, stick a 1 under it. I'm going to use a multiplication dot to change this from division to multiplication, and I'm going to compensate, all right, by forming a reciprocal, flipping this. All right. So it ends up being 6 over pi. All right. Now, as with traditional fractions, right, if you see, here's just an analogy, similar looking features, all right, above and below the line, as in the case of, let's just say 3/4 times 1/3, there's nothing wrong. There's nothing wrong with just simply doing brute force top times top and brute force bottom times bottom, and then simplifying as an afterthought. All right, something like 3/12 would be divisible by 3 and 3 when you get 1, and you get 4. 1/4 would be the end result. Or you could strategically cross cancel. All right, that's basically what you're going to do here, and that isn't that great because look, you could cancel out the pi's. Doesn't happen 100% of the time, but it works in this case. All right, then it is really just a matter of doing brute force top times top and getting 12. All right. And in theory, there would be a 1 here, but that's the same as just simply saying 12. All right. What does that mean in terms of the period? The period is 12, right? If it were some specific unit, you know, like seconds, then you would say it's 12 seconds. If they don't give you a unit, you could just assume it's 12 units, all right? 12 units of time, essentially, all right? Okay, not too bad, right? That, I think, is the hardest, trying to figure out what the period is. Now, let's say you had something slightly different. I'll keep this model here. Suppose you have this as an example, all right? Given y equals -4, the sine of this function, just x, all right? Find the amplitude. Hopefully that's not too faint. All right. Once again, compare the thing that is given to you to the model that we have established, right? What's sitting in the position of amplitude, all right? The A value, right? Now, do remember, this negative that's sitting here is just saying that the sine function is upside down, if you were to draw the picture, right? But it doesn't matter. The amplitude is consistently the same, whether it's upside down or right side up. How long is the distance from the median up to the maximum? It would be the same value in theory as the distance from the medium, the midline, same difference, to the minimum, the extremum. All right. Well, the formula is just simply this. All right, to calculate amplitude, we take an absolute value of whatever the number is sitting in the A position. So if we recognize that this is -4, then the absolute value of -4 is just 4. All right, 4 units, whatever it is. All right, it's probably just really it's just a number. All right. Okay. How would you translate that? It basically means that the wave is stretched vertically. How come? Because if the wave is normally at a maximum of +1 and a minimum of -1, right? If instead the height of the wave goes up 4 times as much, as 1, 2, 3, 4, then you would have a wave that is distorted in this respect. It's just much taller than it would normally be. All right. In addition to that, because it happens to be a negative here, this would be flipped upside down. All right. Okay. Just to complete the thought from before, I mean, it wasn't asked, but what does a period equal to 12 mean? All right. It means that it basically takes 12 units of whatever amount of time to complete one cycle. Okay? The normal period is just simply 2 pi, right? But because of the b value that was given in the other problem, right, it distorts the picture slightly, right? So it ends up taking 12 units versus 2 pi. Okay. Moving along here. Okay. Let's say that we had a calculated phase shift. I really shouldn't have erased that, so I'm going to put it back. Here's the model still. Suppose that if you were given something ugly, again in function notation, yay. Okay. The sine of x plus pi over 6, right, minus 2, to determine 2 things. The phase shift and the vertical shift. Okay. So I'm going to look for the phase shift and the vertical shift. A couple of things to remember. The phase shift. That really comes from this ratio. C over B, which if this happens to be the amount of 1, we'll reduce this to just C, which means that you would have to look at the C value, right, in the drawing, right, in the example here. In this. Okay. The vertical shift is really another way of saying the midline, which is really just referred to as D. So we need to do basically 2 examinations, right? And maybe a little bit of quick calculating. Right. Incidentally, phase shift is really horizontal shift, right? It's funny how this textbook that I stole some of these problems from, it kind of shift, for lack of a better phrase, right? around themselves, right? They'll call it phase shift and then not refer to it as horizontal shift, but that's what it is. And then talk about a horizontal shift, pardon me, a vertical shift, but not refer to it as midline. It's inconsistent is what I'm getting at. Anyhow, vertical shift is midline by another name. Phase shift is horizontal shift by another name. Right? That means, where are we looking? Right? Well, normally just here and here, right? But because of this formula for the phase shift, i.e. the horizontal shift, right, we're going to need to examine the b value too, if there is one. Right? That is the coefficient of x. Right? In the example, if there's no coefficient written here, what would you naturally assume it to be? 1, right? Can't put 0 there because then there wouldn't be an x either. So, we do have that situation. We have a b value of 1 here. Right? And next we're going to look at the c value. Well, in this example, it's this. Right? Let's see. Right. Remember, it's counterintuitive when you're considering the phase shift, right? The horizontal shift, right? So if you see a negative, you associate this with towards the right. Right? Instead, if you see a positive, you're going to weirdly associate this with moving left. Okay. I have to just adjust something in my little notebook here. Okay. Alright. So, anyhow, the bottom line is you're going to put pi over 6 here and just make it negative because it's written as a positive and it's counterintuitive. Alright. That means that it's basically just this. Negative pi over 6. What does that mean? It means that the graph is not distorted. It's not distorted. It's the same ordinary waveform. Right? It's just shifted horizontally, right, to the left by the amount pi over 6, right? Think of this in terms of a number of degrees. 30 degrees shifted over slightly, right, towards the left. So if you had a wave that normally starts out here at, let's just say 0, the whole wave would be shifted towards the left backwards, right? So it's still the same wave, but it would be shifted over by pi over 6, right? It would peak in different places. All of the relative points, right, would be shifted over by that amount. Right? Pi over 6 shift, 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 right? And you'll have this blue sort of waveform rather than the original red type. Right? It isn't distorted, it won't be elongated, it'll just be scooted over. Okay. That's just considering that one alteration, that one chunk of transformation. What if we, at the same time, have a vertical shift going on? This apparently we do because look what's here, right? This is completely dried out. I hope that's not a new one. That would be shameful. Okay. What's sitting in the D position, i.e. the vertical shift, or the midline position of the transformation model, is simply the number -2. Right? All right. So if D is equal to -2, all right, that means that the wave is not distorted either. There's only amplitude would distort the wave vertically. All right, just shifted down 2. All right, So if normally d is equal to 0, essentially, right? If you see a -2, that means that the waveform is not distorted vertically, it's just shifted down slightly, 2 spaces, if you will. Right? If you drew a picture, again, it would look like this in tandem. Okay, sorry for the sound effects. Right? Here would be the usual points of a wave, that is a sine wave. And if you scooted it over each one of these points that are the key points by the amount of pi over 6, that isn't distorting the wave, it's just shifting it to a different location potentially. Right? Let's see. So it might look something like this. From having done just that much of a transformation. This is starting to fade out on me too. Right, now, if in tandem with that, right, you then shifted the wave down, right, by the amount of -2, right, that means the midline and all of these key points, right, would be moved as well. Let's just say that this is -1, this midline is 0, and this is +1. The midline would go to down here. This is probably slightly distorted from lack of graph paper. But let's see. Your midline, if this is now -2, your picture would look like this, roughly. Okay. Let's see. And a little bit further down as well. You'd basically have a wave that is shifted over in blue and then down in green. Right? It would be out of phase. Maybe the end of that one too. And the greens always go fastest. You would say that this is out of phase. Right? By pi over 6, which remember is realistically 30 degrees, right? You scooted over 30 degrees and then shifted down the amount of 2. Okay? So this point is not necessarily on the axis. It's just, for lack of graph paper, I'm just kind of muddling through here. But it's definitely that way. Okay? Alright. We're at 118, okay. Do maybe 2 more examples with you here. Let me give you a drawing. And I'll try to put it on graph paper so it'll be ultra precise here, but let's see. I'm gonna erase this. I should do maybe skip ahead a little bit and discuss basically setting up your calculator. I could confirm or deny the precision of my little drawing I did here. Alright, so look at this for a moment. Alright, there's this handout for setting up your calculator. If you wanted to set something to radians, all right, this would be the procedure. You would have to go to mode, all right, scroll down to radians, make sure that it's highlighted, and then press enter. All right. And then hit second mode to quit, I suppose. All right, so I'll do that now, all right, to verify. All right, my mode to start with was in degrees, was the last that I had it. So I'm going to purposely put this in radians. All right, so you see that it's highlighted like so. All right, second quit. Okay. The next thing is, I'm going to go through the analogy I often mention, which is that if you want to adjust the screen on your calculator, all right, there's more or less the manual and the automatic transmission, if you will. All right. When you want to force the screen dimensions to be whatever uniquely you want them, you're going to go through the window button. And that's basically what we're going to do now. If you want to trust the calculator that it will give you something that is a decent picture without thinking too much about it, all right, go through the zoom feature. All right. A couple of things. If you do go through zoom, all right, one of the features is trig. All right, you might start with that instead of standard. Could try zoom fit as well. All right. Or if you know something is just in the first quadrant, perhaps, choose quadrant 1. I prefer to manipulate it a little bit more control, which is window. All right. Anyhow, the description of basically how to set up a coordinate plane by forcing it, all right, is to go through window. All right. I would start with this. You can always change it after the fact, but you're going to set what the X minimum is, which means how far to the left that the screen would draw, and the maximum X, which would be how far to the right that it draws. All right. What the unit of the increment along the x-axis would be, all right, which will make it pi over 2, 90 degrees, all right. Then the y minimum and maximum, how tall the picture is, how low the picture is. Do the minimum first. I just suggest using -5. It doesn't have to be. Use some whole number. So like maybe start with 2 even. It doesn't have to be 5. All right. Then the scale for the y, just make it 1. And the resolution is just 1. All right. Then press second mode to quit. So I'm going to do that now, right? And then I want to see a finer drawing than the one that I had just done. So here's how it is out of the box, right? It's pretty much 10 and 10, all right? Since I'm now in radian mode, I'm going to make the x minimum -2 pi. So 2. And then to get pi, there is a pi button here. If you see where the caret is, this upward pointing arrow, behind it in blue, at least on a TI-83, TI-84 it's blue, hit second and then press the caret button. And it will produce the pi symbol for you. It will naturally, after you hit enter, it will change it to a decimal, but so what? Right? The maximum is +2 pi. The scale is, x scale is pi over 2. So pi divided by 2. Let's see, negative. Here again, the minimum for y, I'm going to just use -2 for right now rather than 5. It might be a little bit too far away. All right. And, well, you know what? In the case of the last problem, let me try 3, because I think I'm going to need to. All right. As it dipped down, the midline shifted vertically. Let's see, maximum, just make that 3 for the sake of consistency. Scale is 1, resolution is 1, all right, and that's it. Okay. I had some drawing in here last time, I'm going to delete it. Okay. All right, the last thing was this drawing. The function of, what was it, sine of x plus pi over 6 minus 2, right? Okay, I wish I could project this. Why not type this in? If you want to do trig functions, remember you have buttons that are preset to sine, cosine, and tangent at least. So hit sine. The x tau theta button is automatically x plus, and then again hit second in caret if you want to get a pi symbol, divide by 2, close the parentheses, and then put subtraction symbol rather than the negative, which might be intuitive one way or the other. All right, and let me just visually check this. It looks like it's correct. Yeah, it's fine. You don't have to have that. Okay. And hit graph. All right. And you'll see how it draws here, which is pretty. All right, isn't that cool? All right. It is basically as it was expected from my scribble that I did before. Shifted over slightly, okay? And definitely down lower. All right, here's the increments of -1, -2. The midline is the D value, that would be -2, all right? Just to sort of give you some satisfaction, I'm gonna put in, just underneath this to superimpose it, the midline. So I'll put -2 here. I should just put that negative. And you'll see that, all right? Here's the midline in theory, all right? It's at y, -2. That makes the minimum -3, all right? And the maximum is now -1 instead. If you want, you could hit trace, all right? And you'll see what the value is for all of these. Let's see the x values. They're unfortunately in radians, which are a decimal number. And you get the idea. Okay. Let's maybe for comparison superimpose a regular sine wave as well. So I'm just going to put sine of x in here. And you'll see that drawn in its normal places, like so. All right. Notice that they're very similar. All right. Here is usually the starting point is here. The upper, where my finger is pointing, is sine, right? Notice that it's almost the same wave, right? But it's just ever so slightly out of whack. It's out of phase by the amount of what would be 30 degrees, pi over 6, right? Maybe what I should do also is I'll draw it with just that one change, right? So I'll draw this much of it. So you'll see all three, the original sine function, just the horizontal shift, and then with the vertical shift, you'll see is the third thing. If I were a good guy, I would have completed this thought. Okay. Let me see. Sine x plus pi over 2 only. Okay. And then I'm going to hit, watch as it comes into resolution. That's the complete transformation down at the bottom here. Okay, there's the midline. Here is the original sine wave. And here is the sine wave that is just ever so slightly out of whack, right? It's kind of pretty actually, right? Notice where the peaks are, right? It's probably not exactly the way I had drawn it. I think my drawing was a little too sloppy, quite frankly. But you see that it's scooted back, right? I have to sort of look at it too from this angle. Here is the original sine wave, right? And here is the peak of just shifting it horizontally, right? There's a difference of what should be 30 degrees between these. All right? I'm going to hit trace because I'm curious. See if I can get to that top one. All right? It labels it at least. You can see this. And here is regular pi. At this location, that should be 0. It is. You see that it's 0, 0. All right. I'm curious what the what this point is here. All right, for the first transformation. So I'm going to go back to that one and scoot this down to the point of what would be 0 for the x, 0 for the y dimension. And it's a little bit tricky to get that, but something like that. 1.6 pi over 6. All right, let me see. There's 0.5. Belaboring the point at this point. Pi over 2 is 1.5. That's 90. Okay. My thing, actual pi over 2 is 1.57. Right. If in the graph, and it's probably imprecise anyway, because that's just the nature of these calculators, when they have the decimal number here. Right. You'll see. Trace. This point here is 1.6. Right. It's not quite 0 for the y value. If it was exactly 0, it'd probably be pi over 2. Right. We're very close to it. Right. Anyhow, that's how you would set up your calculator. Quit. Let me do 2 more of these, and then we'll stop. Okay. If you were given a drawing given the graph that looks like this. Let's see. I'll sort of draw this as best I can. And in blue, I'll put this here. You know what? Let me try that. I don't want to drive you crazy, but I want to see if I can finagle using my graph paper rather than simply doodle these. And that will make it a little bit more satisfying drawing here. I have a little paper clip here. Sort of paper clip. Okay. And where's my markers here? These were the duds anyway. Okay. Suppose you were given a graph. I'll write that again. That looks like this. I'll do it maybe in red because it's more prominent. I'm gonna make it like that. I'm just drawing this dashed line to serve as where the median would be, the midline. This is usually here, i.e. the D value, and this is the midline now, right? And let's see. Gotta be consistent when you draw these things, at least if you do it nicely. And the increment will be a little bit out of whack too. Right? The increment will be pi every 4 boxes. I'll just draw this as pi. Is that in the frame? It looks like it is. Let me just pitch this ever so slightly. Okay. Be consistent if you're doing this on graph paper. This will be 2 pi. And 1, 2, 3, 4. This will be 3 pi. 1, 2, 3, 4. 4 pi. And if you're doing this on graph paper just to get through it, to start with, you could use your calculator certainly, but sometimes drawing something makes you learn it a little bit better, which is the only reason why I'm trying to go through the motions. All right, put a dot here at this point, right, which would normally be the origin. At pi, all the way up here, right, and these are incremented sloppily. I made it 4 boxes tall, and I want it to be consistent. At the point of pi, put a dot here, and then a dot at 3 pi, and then at 3 pi again up here, and then technically 1 at 4 pi. And then going backwards, 2, 3, and with this negative pi, 1, 2, 3, 4, negative 2 pi, you don't have to go that far, but let's see, at negative pi, put a dot here, and at 2 pi, let's draw this much of the wave, right? It'll stretch into infinity, but if you have a wave that basically is cycling like this, hint darker, but let me see. And lastly, fill in these labels. All right. If the height at the midline is 1/2, right? That's 0.5, right? Then if this is even this way and this way, this maximum is equal to +1, right? And this minimum is equal to 0 instead. Okay. Given this graph, right, what we'll do is identify the sinusoidal function. Sinusoidal is just another way of referring to it as being a wave, right? That it repeats like a sine wave, or cosine theory, right? So what I would do is start with the model, right? And then try to pluck out the relevant information from this drawing. Sine. All right. I'm going to duplicate this twice. And give you a little bit of advice. Okay. It probably doesn't matter which one of these models you use, the sine or the cosine, but which would you say that it most closely resembles? Right. If you looked at it from here moving forward, would you say that this looks a little bit like if I drew normally a sine wave? I'll put this, I wish I had a different color, green, and I very faintly draw this. If I drew this waveform just underneath the actual blue one, you know, this thing in green, right? You notice that the extrema, the minimums, if you will, start in the same place. So if I had to choose either a sine or a cosine to start with, all right, which one would you say does this more closely resemble, all right? What does this green look like? This green, this is a very bad color, is basically the cosine function. So I would go with this just because the minima, the minimums in English, minima in Latin, all right, start in the same place. This more closely resembles a cosine than it does a sine. If you went ahead with sine, you may have to tweak it a little bit more than you would need to. So I'm not going to use that. All right. I'm going to go with this, cosine. Okay. Well, let me erase that because it's getting in the way. Let's see what information we could glean from this. We know that we have to basically figure out what is sitting here, what is sitting here, what is sitting here, and what is sitting here. All right. The easiest thing to do is not necessarily A, B, C in alphabetical order. The easiest thing might just be, well, if the graph normally is riding along the axis, that is the midline usually, and that is y equals 0, that's the x-axis. What is it now? All right. Look at this dashed middle line that you see here. All right. It's 1/2, all right, which is, if you wrote it in the style of a decimal, 0.5. All right. That means that in this location for D, all right, I'm going to definitely put the number 1/2 or 0.5, and probably it's the decimal, I would assume. All right. But I have to choose, all right, is it positive or is it negative? Well, if it is shifted up like this, I would assume that it's positive. So in place of D, I'm going to put 0.5 to fill in this skeleton here. That much has been accomplished. All right. D is equal to 0.5, all right, which is a y value really. Okay. Well, you can call it a half. Okay. All right. Now maybe do the amplitude. Let's get A. Remember, A has to be an absolute value. We could consider whether it's, well, this is the difference between having gone the sine route or the cosine route. All right. Since we went with cosine and the extrema were in the same starting place, namely the y-axis, right? The minimum of the function, the transformation, and the minimum of the usual form of cosine are in the same place, right? In terms of x, all right? We don't have to worry about it being reflected at all, right? Anyhow, we have this formula: 1/2 the max minus the min. Okay. The minimum is now equal to 0, as opposed to being -1, right? So we're going to put 0 for the minimum, right? The maximum is now at +1. Okay. So what is the difference of 1 minus 0? Well, it's just 1 naturally. What is 1 times 1/2? Right? It is just coincidentally the same thing. It's 0.5. Right. So your A value is 0.5 also. quick. Okay. The number of 0.5 would sit here. Now there is one thing I did make one little mistake, I realize now, right? Cosine, although it does start in sitting on the y-axis, right? And if it is just tracing out like this, would be in fact like this, right? Right? But where's cosine under normal conditions? It is actually reflected, all right? Right. Let me just doodle cosine for reference right here, because I don't want to misinform you, right? What is cosine normally? Cosine does start on the y-axis, but it is like this, sort of this script V shape, if you will. What we have is something that starts in the same place in terms of its x value, sitting right on the y-axis, ironically perhaps, but it is vertically reflected. All right? It is that V shape. All right? But it's upside down. All right? It is in fact upside down. Right. So if we had to associate a positive or a negative sign, it would actually be appropriate to make it a negative. I'm sorry. Okay, so a negative 0.5 up in the front. It's getting sloppy, so what I'm going to do is I'm going to erase what I ended up not using just above it and duplicate part of the scribble right here, at least as much as we have filled in. A negative, because it is actually upside down, right? Cosine would be like that instead, under normal conditions. Okay, and we determined that the amplitude is 0.5. We're using cosine because of its starting point is where cosine would normally be in any event. It's normally sitting right on top of the axis like this, right, at an extrema. In terms of, to say, the minima start in the same place, what I should say to augment this slightly is be a little less vague. All right. By the same place, I mean that it starts, that you have an extrema that is either a minimum or a maximum, right, at x equals 0, right, which is the y-axis. If your max or min start in the same place in terms of there is an extrema and extrema, right? In the normal case, it would be a maximum. In this case, it's a minimum in blue, right? That's x equals 0, that's y-axis. That's why I chose cosine, okay? This happens to be negative because it's reflected. Okay. Now we still have to determine the B, the C, and this 0.5 is legit sitting here. Okay, how's that look in the frame? Good. Right, let me erase this, as that is now duplicated. Right, and we'll continue with all the work here. If you examine the increments along the x-axis. This is 0, this is pi, and this is 2 pi. I'm going to trace it in black, unfortunately, just because, and I'm saying that just because I have so many different colors on top of the black grid lines to begin with. And if I were to trace out a regular incarnation of cosine, right, from before, I'll do it down here. I'll put a little scribble here to compare notes. Right? Regular cosine looks like this. And I have to make sure that I use it the appropriate increments here. Okay. For the sake of analogy. Never mind the amplitude for a moment. This is, for all intents and purposes, regular cosine here. Right. The increments that I had you draw before are now going to come in handy. So basically, this diagram, all right, for cosine, all right, remember those increments? 0, pi over 2, the minimum is pi, the next number is 3 pi over 2, and then the maximum would be 2 pi. Notice that this is basically the same, all right? I'd rather not superimpose the two pictures because unfortunately it's getting a little messy with the grid lines, all right? But at the location of the end of this complete wave, all right, you are at the location of 2 pi. At the location of the middle of the wave, essentially, is pi, all right? At the location of the start, it's 0, all right? What that means is that even though it has been vertically reflected and potentially stretched, right? Maybe it has, or squashed actually, because it has an amplitude that is a decimal number. It's been squashed slightly. This is not drawn to scale in terms of amplitude, this black curve, all right? What that means is that this has not been shifted horizontally one way or another, right? So what you could say when you're filling in the transformation model, because we did D and we did A, because those are the easy ones, right? When we're trying to get after B, all right, B we could assume is just the number 1. Right. How come? All right. We could assume that B is equal to 1 because it isn't actually horizontally stretched or compressed. Right. Right. It completes the wave in the same cycle. Right. This is because it's not horizontally stretched or compressed. Right? And how do I know that? Again, because it completes in the same 2 pi. It completes in the same wave cycle. The cosines and sines, all right, have a wave cycle, a period of 2 pi, all right, in both cases, all right. This, although it is apparently changed vertically somehow, is not changed horizontally. Alright, so you could assume that B is equal to 1 for that reason. Alright, it's not stretched, it's not compressed. It completes in the same waveform. Alright, that means that this is essentially a 1 here in the model, which means you could neglect to write it, you could just leave it as X. It would be more concise. Alright. The last thing, and this is kind of part of it, is the C value. All right. You know that C is dependent upon B, all right? And if B is 1, all right, from that formula, then what you really just have is C. This starts in the same place, all right? In terms of the x is equal to 0. It's not shifted one way or another, and it isn't stretched or compressed, all right? So the horizontal shift is 0, right? Because it's not shifted. Okay, in comparison to the norm, right? You don't see an extrema in some other location shifted to the left, shifted towards the right, right? The extrema, in this case it's a maximum, and in this case it's a minimum, start in essentially the same place in terms of x, right? So C is 0. To write it most concisely, this is what you would have. And I'll take this out now. This waveform, although it does take some doing, can be most concisely written as this is a function, you can call it y, of negative 0.5, right? All right. The cosine of x plus 0.5, coincidentally. That's the solution. All right. Reading the graph obviously takes adjusting too. And it's negative as it's reflected. Okay. One more of these, right? That's taking a picture, all right, and translating it into a function. Let's say that you are given a function and you want to translate it into a drawing. Yes, you could use a calculator, right? Let's just try doing it by hand one time. Times it. Going over a little bit, that's okay. Okay, let me put this back. I'll put this piece of black paper here. Okay. Suppose this is your example, all right, that they ask you to sketch the graph of this function. The function is equal to negative 2 sine of pi over 2 x. All right. And again, beneath it, I'm going to put the model just for reference. A sine bx minus c plus d. All right, you'll see what is included and what is not included. I'm going to have to sort of draw little increments, right, as quickly as I can. All right. I'm just going to make it 4 boxes each, like that. And I'll do the same thing here. Sorry, blocky, but it's okay. In red, I'm going to draw a sine wave as it normally looks. All right. If this is pi over 2, and this is pi, and this is 3 pi over 2, and this is 2 pi, and this is just positive 1, and this is just negative 1, and I should have dots at these respective locations. And this would be the wave And if I did it backwards, just really quickly, this is probably overkill, but hey, better to be safe than sorry. Let's see. Negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. We would have dots at these locations. I'm going to just faintly draw this in. I'm just going to draw that very, very faint, like Bob Ross, I feel like now. Okay. That's what it would be if you stretched it backwards. Right. Sometimes when you have to draw something, you need to go a little bit forward, a little extra backward. Now, to compare what is given to us in black here with the model that is in blue, all right, you'll notice that there are some features that are included from transformations and some that are not. All right, there is apparently no horizontal shift, all right, in this case. No phase shift, all right, that's another way of calling it. And there is no D value here, so there's no vertical shift, which means that the midline is y equals 0, as it normally is. Okay, the only things that we have to pluck out of here, therefore, are the value that's sitting in place of B, right? Which is angular frequency, or what we might call horizontal stretch, or compression, all right? And eventually the amplitude, and the fact that this is reflected. This will be a negative, so it'll be upside down in theory. All right. Let's see. Let's start with B. All right. All right. Normally, how would we calculate B? We would calculate B from a period of 2 pi. All right. All right, the number of waves that are completed in 2 pi. All right. Let's see. In this case, all right, our B value, all right, is just what's sitting here, all right? All right. So if B is already given to us as pi over 2, all right, what we can infer from that is this instead. The period formula, all right, is this inversely proportional. Remember, period is inversely proportional, all right? So if period is normally 2 pi, and we now have a B value that's sitting here as a denominator, and I'm just going to insert this in place of B, pi over 2. All right. If we straighten this out, all right, remember it's division again. All right. So you would end up with 2 pi, although this is called 1, divided by, as it is originally oriented, pi over 2. All right. I need the space, so I'm going to erase this. The outcome of this is, again, keep, change, flip. You're going to flip this upside down, which means that it's going to be 2 on top and pi on the bottom, and you're going to multiply instead of divide. And there's going to be a natural cancellation effect. And this is going to cancel the pi's, and therefore the period, the time it takes to complete one cycle, one wave, one cycle, whatever you want to call it, one full wave cycle, is just the amount of 2 times 2, which is 4. Okay. All right. My increments are going to be slightly thrown off then, all right? As if I translated these to decimals, all right? And in theory, you would have to do that if you were doing this by hand. All right, let me just show you, just this one time. All right. Pi divided by 2 in the style of a decimal is 1.6 roughly. All right. Well, I'm going to just kind of cheat. And I say, well, that's 1.5, 1.6 approximately. All right. A whole pi is naturally 3.14. So let's just call this about 5, since I'm doing this by hand, and this is about 3. Right? And therefore, this is 3 pi over 4 is about 4.5. And 2 would be 6.28, so this is about 6. Right? All right. What's going to happen then is that if it normally takes to the amount of approximately 6, because that's what 2 pi is normally, but instead the wave, the time it takes to complete one full wave is 4, right, units. Right. It's going to be squashed slightly. Right. So if this is about 4.5 and that's about 3, right, you're going to have a dot. 1, 2, 3, 4. Let's see, how much is the difference of that? 1.5. No, turn it off. Bear with me 1 sec. 1.5. I'm trying to be as precise as possible. 3/8. Okay. 6. 1/8. 4 is going to be basically just about here. Right? That's 4. Right? That's basically this dot now moved to here, backward. All right, almost 1, 2, 3, 4, 4.5, almost that way. Next one, the dot that would be here would be 1, 2, 3, 4.5, roughly there. All right, shifted this way. All right. All right, and this one, no, I'm gonna say, I gotta correct myself, sorry. I'm really forcing it here. The wave is going to start in the same place, but it's going to end here. This is where it ends now. Right? So essentially, it's still going to ride up to this line here. It's just not going to be exactly in the same place. All right? Trying to imagine it a little bit more squashed. No, that's too much. You're going to have something that kind of looks like this. It's a little distorted naturally as a result of that. This is fading. And again, that's approximately where 4 is, and the reason I'm saying 4 is just shy of what would be 3 pi over 2. This was 3 pi over 2 is approximately 4.5 as a decimal. All right, so it's a little bit below that. Normally it goes all the way out to here, right? But instead, it's going to be ever so slightly more squashed, right? And it will still land in the same place, right? Okay. Now the next thing is that it has an amplitude, right? Which is this A value, right? If the A value is negative, pardon me, let's just start with 2. Instead of it going up to 1, right, which is what it would be normally, this is now going to be peaking up to here. Right? If this is positive 2, right, let's see. You're going to have a picture that is squashed like this then. Sorry, I'm using red so much, but it's the best color, really. Okay. Last thing is that this is now negative, which means that it's going to be this upside down. So though I'm thinking it's going to be a bit problematic, because green doesn't ever show up nicely. Why do my greens die so quickly? I don't know. Just picture that something like this. Let me draw it in black. Another dud for green. Let's see that one a little bit better. Save that one. That one is just terrible. It's definitely getting thrown out. All right. The end result, right, would basically be this elongated vertically and flipped upside down and squashed horizontally, compressed example of the waveform. Right. So it went from the full red here to squashed to the blue because the time it takes to complete one wave cycle is smaller. I could be a little bit more precise, but I'm just trying to get this to be basically like it should look. All right. And then, after it's being compressed, horizontally, it is stretched vertically, and then flipped upside down. So, compressed to the point that it is blue here, stretched, right, to the point that it is red, sadly, in here and here, and then flipped like this. The end result looks like something like this. I'll erase all of the extra stuff so you can make it a little bit easier to see, hopefully. This other stuff is not necessary apparently, but that's basically the end result. Okay, now since you're more likely going to do this with the graphing calculator, all right, we already have the calculator set in theory, again according to these instructions, all right, setting the screen dimensions to pi radians and then actually inserting it. All right. This is a list that basically had to insert any trig function in if you want. All right, I'm going to do that now, and I'll show you what the end result, and we'll see if it compares to my sloppy drawing here. And then I got to clear out my old stuff. Okay. I think my calculator needs new batteries. Okay. So, if the original function is -2 sine of pi over 2 with an x attached. All right. Remember, use this negative for the coefficient. So it's 2 sine, and then if you want to get pi, hit second and then the caret. It shows up pi. Divide by 2. All right. What I should probably do, and I wish I would have did it to begin with, is when you enter something in the style of a fraction, as in the case of pi over 2, all right, you might want to isolate it in its own parentheses, unless you go through the function that allows you to enter things intuitively as a fraction. What I'm saying is, even if it seems superfluous, all right, put in a parentheses and write it like this, where you see that it is essentially a parentheses within a parentheses. Reason being, when you put the x variable next to it, and that is a fancy phrase. When you put the x variable here, which is this button tau theta, you don't want it to think or potentially think that the denominator is 2x, right? Because it's not that. It would technically be pi attached to the x. If you were to take this and kind of condense it rather than have it separated as a coefficient, it would technically be that, right? Not the x as a denominator. You got to be careful of that. That would change it drastically, right? So you could enter it this way, right? Which is probably what every calculator would automatically do, right? Or if you have updated software, right, you can enter it slightly more intuitively, like this. If you hit alpha, we can go through the math button, and then alpha, and then F1, the green. F1 is this y equals button, the function behind it. You see that you have something that says n/d. All right, that will allow you to enter something intuitively as an obvious top, a line, and a bottom. So I'm going to go with that. And then you see that it shows up as a natural fraction. Okay, so second, and then pi. And then I'm going to scoot over with my calculator's arrows. And now I have it written more intuitively. So I'm going to put x. And then I'm going to be a good guy and close the parentheses. And they have that. Right. Now as I hit graph, pay attention to, basically, I have a missing fingertip, I'm sorry. My hand got stuck in a door when I was a kid. Anyhow, if you pay attention to that much of the graph, you know, kind of like move it out of frame there. There you go. Special effects. Notice that it is upside down. And it stretches into infinity backward. You could change the screen dimensions if you want. All right, and it would go a little bit past it if you had more of the picture. But usually this is how much you would see, which is that terrible drawing. All right, what I should do also, to emphasize, let me draw just underneath it a regular sine function, and you'll see it superimposed one or the other, how it's different. Sine of simply x. All right, typed like that, all right, and then graph. All right. Notice that the transformation is taller because it's vertically stretched, all right, and that it ends in different places. I wish this was in color, but if you look over here, the wave starts at the what would normally be the y-axis here, and it ends over here, right? These increments, although they're not labeled, right, if you hit trace, all right, you could move along, all right, and see what this correlates to in terms of an x value and a y value. That location, right, is about 2 on the transformation, all right, 2.00, right? It's halfway, it makes sense because the period is 4. And if you went all the way to the end of the single waveform, went a little bit too far, here's where the cursor is. Notice where it is. The unfortunate downside to the graphing calculators is that the screen is not really precise. So it's hard to get it exactly on that point. If I press 4 right down here, it'll give me the more precise measurement for y. Y is 0 at the location of 4. Okay. Anyhow, the point is this stretched out vertical waveform, all right, different from the flattened waveform, which is normal, ends in the place that we predicted, x equals 4. All right. That's the period. One complete wave, even though it's stretched vertically, ends up stopping at this point. All right. That's how long it takes. Now, normally, all right? You see this curve here that is the flatter curve. That's the normal sine wave. If I went all the way to the edge of the screen here, that would be one complete waveform of that. That's 2 pi, all right? So I'm going to scoot over there, and you see how the x dimensions change. There we go. It's approximately there. It's probably just a little bit smidgen above it. But look what you have, all right? 6.01, all right? It should be what? If it's 2 pi, it should be really 6.28, all right? And you'll notice what the y value is. It's not quite 0 when it really should be 0. So I'm going to type 2 and then exactly pi. And you'll see that the y value should be exactly 0 here. It gave me an error message because of the screen dimensions. I have to change this stupid screen dimensions. Excuse me a minute. Here, back in the window view, I'm just going to stretch this out a little bit further. See, because actual pi is 6, but this is exact 2 pi here. Let me make this 3, okay? And now I want to do the graph, all right? I went... I made the minimum, x minimum, the wrong thing. Back. Okay. 2, negative 2 pi. Okay. 7. The maximum, I'm going to just change the screen dimension. If you get an error message like I just had, the reason why it's giving you an error message, even though you didn't technically do anything wrong, I didn't, is because the screen dimensions was manually set to exactly 2 pi. It goes into convulsions if you don't adjust it so that it technically would be a longer view. So I'm going to go slightly higher than 6. I'm going 7. And now I'm going to graph, right? Here is the transformation as we had predicted. Here is actual sine as it should look, chasing along. And I was trying to prove a point here. I'm going to scoot along here. That's 4. The one complete waveform completes in 4 units, right? Which really should be 0. Again, if you type 4 here and then hit enter, you see that's what y equals 0. But if I go all the way to the edge, right, you'll see that this is 2 pi like it normally is. It's a little bit too high. All right, 6.0. Again, if I force it, all right, to do a precise calculation, 2 for x, and then I'm going to hit second and then caret for pi. This is 2 pi, 6.28, whatever it is. You'll see that it should spit out, as it's rounding is the problem here, close to 0, but it's distorted slightly. And a pain in the neck. Oh, because it's on the wrong graph. Okay. Here, all right. 6.29, all right. It's supposed to be 6.28 something. All right, notice what y is. Y is almost exactly 0. All right. Unfortunately, it's being a little bit finicky. All right. If I switch functions, like this is the transformation, this is regular sine. You see that it changes up here. All right. Now I'm going to tell it 2 pi. All right. Y is equal to 0, as it's supposed to be, because a sine completes normally in the amount of 2 pi, whereas the transformation completes much sooner than that. If 2 pi is 6.28 approximately as a decimal, our transformation completes at 4. All right, 2 pi would be out here. That's what I'm getting at. All right, anyhow, use your calculator, all right, when you're doing this. All right, just realize that sometimes it's a little bit finicky. Okay, that's it for now. All right, like I said, try to print out those pages that I give you. This one, terminology, And this graph, just as have a reference for cosine and trig, what they normally should be, especially if your calculator's giving you a hard time like me. Let me continue with this. Leave this here. We're going to come back on Thursday. All right. I'm going to start with section A2, which is the graphs of tangent and the other trig functions. Okay. All right. Thank you guys. All right. See you on Thursday.